Okay, the second gas law that we're going to be dealing with is Charles's law. Make sure that you've watched the video before we get into it. And when I say the video, of course, not this one because you're looking at it now. The Science Guys video, same guys who did the Boyle's Law video. They're very good. All right, so in this particular gas law, we're looking at the relationship between temperature and volume. And when they put the balloon into a freezer, it shrank, and when they put hot water over on top of it, it expanded. So that means then that when they put it in the cold, they decrease the temperature, which decreased the volume. When they put it in the hot water, they increase the temperature, which increased the volume. So they both went down or they both went up. That is called a direct relationship. So if we show this mathematically, the concept here is volume is directly proportional to temperature. We can write it this way, or temperature is directly to volume. It really doesn't make any difference. Okay? Now, I'm going to use this one because the formula works out that way, but we could have used the other one, and a different formula will work just as well, which I'll show you in just a little bit. So, like last time, we have a proportionality here. This is called a direct relationship or direct proportion. So there's no fractions involved like there were for the indirect relationships. So we replace the alpha there, which is the proportionality constant. We replace that with an equal sign. But when we do that, we have to have a number that ties the two sides together. And like we did last time, we use the letter K, which is the first letter in the German word constant. And then we multiply that times V. Now, this number is not important to us. We want to develop a formula that's going to get rid of that K. So I'm going to isolate K by dividing both sides by V. And so that means that T over V is going to equal to K. So if we take one set of conditions with the corresponding temperature and volume, which I'll call T1 and V1, we divide those two out, and temperature must be expressed in Kelvin. Remember, Kelvin is degrees Celsius plus 273. If you didn't know that, you know now. But it has to be expressed that way. Why? Because there's no such thing as molecules moving backwards. If you were to have a negative volume, you're implying, say like if it's 50 degrees and negative 50 degrees are the two volume or temperatures involved, you're basically implying, even though you don't really mean it, but you're implying that the direction of motion of the molecules at 50 degrees is exactly opposite of the direction of movement of the molecules at negative 50 degrees. There is no such thing as negative temperature in the eyes of Lord Kelvin, and technically he's correct when we deal with these mathematical concepts. So T1 over V1 is going to give us that constant. If we change the temperature, the volume is going to change, or we change the volume, the temperature is going to change. That gives me a new set of conditions, T2 over V2. Divide those two out, and again, it's going to give you the same value of K. And as we talked about in Boyle's Law, according to the transitive property of mathematics, if A equals B and B equals C, therefore A equals C, since they're both equal to K, then T1 over V1 equals T2 over V2. And that is the formula that we are going to be using for Boyle's or Charles's law. Now, like I said, we could have flipped everything around. So if you came with V1 over T1 equals V2 over T2, and you're worried that's not the right formula, worry no more. That is exactly the same thing. You're going to come up with the same value. And again, we don't care about what K is, even though K would be a different number, it's constant for this equation. It's actually the inverse of the K that we had up there for the other one. So, that all works out. So, the mathematics is going to be based on this. Now this is what we call the qualitative or quantitative definition of Charles' law. The qualitative one, the verbal definition, is simply that as temperature increases or decreases, depending upon which direction we want to go with here, the volume since this is a direct relationship, if we're going to increase the temperature, the volume increases, or as the temperature decreases, the volume decreases. Okay, so let's take a look at a couple of examples that we used on the script there. The first one dealt with 450 cc's of hydrogen gas at 40 degrees Celsius. It's going to have a temperature change from 40 to 60 degrees. So that means that this is V1, this is T1, this is T2, this is V2. Now, before we even start, let's predict what's going to happen to the volume here. So if we're going from 40 to 60 degrees, that is an increase in temperature, and since this is a direct relationship, that means the volume should increase. How much? That's what the calculation's for. So let's do that, shall we? So we have T1, which is 313K, adding 270 to 40. V1 is 450 cc's, equals T2 is 60 plus 273, which is 333K. And we don't know the second volume, that's what we're going to solve for. So this is a proportionality problem. In proportionality problems, we can cross multiply. So we are going to get 313K times V2 equals 333K times 450 cc's. And we want to get the variable by itself, so we divide both sides by 313K. And the 313Ks cancel out here to leave us V2. Now, the Kelvin's going to cancel out here. This is why I prefer that when you do these practice problems that you're going to show your variables and your setups. If you don't, you'll get them back and you'll be asked to put them in. So just keep that in mind as you go through this. But and you can see after the cancellation of Kelvin that the answer can't help its cc's if you're ever concerned or confused as to what the label should be. And when we work this out, we get 479 cc's. Okay? Second example. We have 65 liters of oxygen as the first volume. We have 10 degrees Celsius as the corresponding temperature to that oxygen volume. We added 273, we got 283K, so that's our V1 and that's our T1. Our V2 is 55 liters. So again, let's kind of speculate as to what's going to happen. Now remember, the formula is T1 over V1 equals T2 over V2. And it's a direct relationship. So if the volume is going to go down, what do you anticipate the temperature doing? Well, because it's direct, they're both going in the same direction, we would expect the temperature to go down. How much? That's what the calculation is for. So let's do that, shall we? Plug in our numbers. 65.0 liters over 283K is equal to 55.0 liters over V2. Cross multiply again because we have a proportionality problem here. We have 65.0 liters times V2 equals 283K times 55.0 liters. And I'm going to get the V2 by itself, so we divide both sides by 65.0 liters. these cancel out, and the liters cancel out, so it's going to give me an answer for temperature in Kelvin, which presents a special problem to us, but let's get through the calculation part right here. If you're going to take these two and divide by that, your answer is going to turn out to be 240 K. But, and here's the issue, we don't have any temperatures in Kelvin. I've yet to drive by a bank that has Fahrenheit, Celsius temperatures on there and Kelvin. It doesn't happen. My lab has no Kelvin thermometers. We don't use Kelvin. We only use Kelvin in calculations because of the fact that there's no such thing as a negative motion of molecules. So we have to subtract the 273. We have to do the inverse of how we got to Kelvin, which is by adding 273. And so when that happens, this gives us negative 33 degrees Celsius. And as we predicted, the temperature dropped from 10 degrees to 33 below zero. All right? Practice problems. You have 5 at the end of the script. Have fun.